In this video, we're going to be contrasting the reactions of alkenes and alkynes. We're going to do several videos on that. All of the reactions of alkenes and alkynes are addition reactions, so electrophilic addition. So we're going to see what is the similarities and what are the differences, particularly in the reagents that we're going to use in each case. So let's get to it. So the first reaction that we're going to be seeing is the typical, we all study Markovnikov addition. So say that I have, I'm going to do cyclohexene, but I'm going to have a substituent. So the first reaction we study, as I said, is hydrohalogenation. And this is proceeds Markovnikov in the absence of peroxide. Markovnikov. And here what we need to remember is that in Markovnikov, we will add the H at the least substituted. So I'm going to just do a little arrow here. And then the X, the halide, is going to end up in the other carbon. The reason for that is that when you do the mechanism of that, I'm going to erase this. It's better to show the mechanism, but I'm not going to do the mechanism for everything. But again, this is like that. And if you add that H at the least substituted, you're going to create a more stable carbocation. So that's the reason here the carbocation is tertiary. So, but the same, if you do this in the presence, if you have peroxides, then the regiochemistry here, you end up having the X here, so at the more substituted, and the regioselectivity changes, and now you're going to have here is your metal, and you're going to have the X here. So the reaction is regioselective, Markovnikov or anti-Markovnikov, depending on the reagent that we're using. Now let's do the alkyne. This is an alkene. We're going to do an alkyne now. Alkynes, you can have terminal. This is a terminal alkyne. And you will have also, there are internal alkynes. So when you have a terminal alkyne, not often drawn, but here there is an H, which is acidic. So terminal alkynes, we're going to be looking at the same reaction. So if we have this, and the reaction proceeds with say, regioselective, also Markovnikov, so in the absence of peroxide. So what you're going to do is add the H at the least substituted, similar to what we did here. But here we're not going to be forming carbocation like that. In the transition state is more complex. And what happens in alkynes is that the rate depends here for this reaction in this is the concentration of the alkyl halide and the say hydrochloric hydrofluoric acid square, the dependence. And it is because the second molecule will assist with the stabilizing the carbocation. But what we need to remember here when we are predicting products is that we will add Markovnikov here. So H here and X here. And now what is different is that say that we have one equivalent. If we have one equivalent, we will add only one H and one X. So we are going to form here an alkene. Now, if you have two equivalents, or say that you're working with X's, what's going to happen is that you will add twice in Markovnikov fashion. So you will, from here, from the alkene, you can do the H here and the X here. So you will end up adding, say, 2 molecules of HX. So your final product will have this. So, and again, regioselectivity is the same, it's Markovnikov, but since you have 2 pi bonds, you can do If you use one equivalent, you do the addition once, and you end up with the substituted alkene here, or in excess of the halide, you produce that, but it's like twice Markovnikov. That's what we have different here. Here you can only add one halide. Now, with peroxide, also we will have the opposite region selectivity. So what we have is that here I'm going to erase the internal alkyne, and I'm going to be working still with the terminal alkyne. So what it is now anti-Markovnikov if this is HX in peroxide. So, and now you will be adding here the H. Now I'm using a different color so that we see that, and the X is going to go here. So you will have a couple of products. You can have this, and here you're adding H. Again, you're adding one molecule here, so you have an alkene. But notice now the X is being added at the least substituted in the anti-Markovnikov. And then you have this alkene, but you can also have this. So that is different from what we would expect in the case of alkene doing hydrohalogenation anti-Markovnikov. You have only one product. Here you will have two. And the major product is the E isomer. Opposite, that's the C. Okay, so that's what's different. So again, in hydrohalogenation, you will have the same behavior, Markovnikov or anti-Markovnikov, with alkenes and alkynes. With alkenes, you have a single product here. Another thing is that in alkenes, we can have this carbocation may rearrange. Not this case because it's tertiary. But typically, if it's not rearranging, we expect that one product. And anti-Markovnikov, this is a product. So the H will be added here, the X here. And in the case of the alkynes, here with hydrohalogenation Markovnikov in excess of the HX, your acid, you will add twice. So first, one equivalent will add one time Markovnikov, so H and X, H and X. You get this substituted alkene, but in excess you can add that twice, and you form a dihalide. That can be used to actually synthesize. You can reverse this and form the alkyne by using sodium azide. And that's one of the methods to synthesize alkynes from a dihalide with excess of sodium amide. We can get that. Now in the anti-Markovnikov reaction, we can have both two products because you can add to the double bond. You can form that E and the C, so you may have that. If this is the case, you will have that E as your major product.